All right, welcome everyone to this talk about full stack Scala. My name is Jonas. Wait, Jonas, full stack Scala? You mean full stack as in including the front end? And yep, as it turns out, you can do everything in Scala all the way to ops even. When I say this, I usually get something like, okay, that's cool, but who does that? And it's kind of a tough one. You know, this is not yet mainstream. It's the main reason I'm here talking, to show that it's really possible, and there are even advantages to do everything in Scala, because who would want the entire team to be able to intervene in all the parts, front end, back end, infra? Operationally, this is efficient. It encourages collective awareness of the whole project. The code base as a whole is leaner. You benefit from code sharing between front and back, and from Scala's expressiveness. No more big quantities of Terraform YAML, Helm charts, API definitions, etc. Third-party library surface is also naturally reduced. This means less update work, less possibilities for regression, etc. And turns out the Scala.js library ecosystem, and I'm thinking here of Laminar in particular, allows for richly interactive experiences. Some say WebAssembly is the future for many applications. Scala.js is ideally suited for that, as Sebastian will tell us also in the next session. Imagine doing AI in the browser, for instance, for privacy-sensitive applications, etc. A bit about my journey. So I've spent 7 years building microservices for the best mile fleet orchestration platform here in Lausanne. This was just a lot of asphalt, actually. And I figured we needed some more trees. So I joined Terrasol, a company with strong expertise in soil science. We sell maps for planting trees in the right place. And I'm now building exomat.com. It's a SaaS for urban renaturation planning. It's still a beta, but the system allows already to show various specialized maps, selecting parcels, taking measurements, etc. And my purpose here is to walk you through a bit through this code base and share of what I learned. So finally, getting a little more technical, starting with the project structure, I'm using Trusty SBT. As you can see, there is a shared project between front and back. In this shared project, we mainly find endpoint definitions using Tapir algebra. That's how we define our API. Tapir is a library from Software Mill to describe HTTP APIs. And this is great to align client and server. More about this on the next slide. In model, we have the data classes of the API together with serialization aspects. And I have a special internationalization namespace here, which I mentioned specifically because we'll use this common use case as a guiding thread throughout the presentation. What I didn't know when I made this choice is how hard it is to pronounce, though. I'll do my best. So this is how you define endpoints with Tapir. Of course, starting with imports, Tapir main import, and also a module for micropickle, which we'll use for JSON serialization. Then we import the data classes involved in the endpoint we will define. We also use iron for refined types, as we'll see shortly, so we import the Tapir module for that. We use a trait for our definitions. This keeps aspects separate and allows for mix-ins. And this is the endpoint that allows for retrieving translations in our app. We express it with Tapir DSL with a path parameter of type language. Then we specify the type of response, and the micropickle codec is picked up by Tapir from the given scope. We'll see how we generate the codec. And finally, we can even specify endpoint documentation. I mentioned refined types. In the system, the language is such a refined type. In our case, we want a 2-char language code, and we only support certain languages. So we use the iron library to define a refined new type. This is a regex to match only certain language codes at the type level. And since we're using the iron module for Tapir, the API will automatically reject requests that do not comply, which is very convenient. Other use cases of iron in our app are units, geographic coordinates, percentage, location slug, etc. All kinds of constraints are possible. And it's at the type level. Compile time validation is supported for literals. So that's very convenient. There is even support for Doobie as well, which is the database driver we use, as we'll see later. So refined types overall grant us high-value safety throughout the system. Here are the data classes involved in this internationalization endpoint. As you can see, we use the type class derivation syntax of Scala 3 for codecs. And since it's in a shared project between front and back, we just have this single definition for it. So now that we have defined our endpoints and types, we can move on to creating the client project, the front end. So this depends on the Scala.js side of the shared cross project. We enable, of course, the Scala.js plugin and also scalably typed. This will allow us to import TypeScript type definitions. We'll speak about this a bit more later. We tell Scala.js that this is an application with a main method. And we also instruct it to emit ECMAScript modules in such a way that they are small for our application, namespace, to optimize the incremental reload experience. And yes, Scala.js can use NPM as a package manager. In fact, it's just a Vite project, and Scala.js has a Vite plugin that makes it aware of the Scala.js build and allows for hot reload. Another proof of that is the presence of a package.json file in our Scala project, which took me a while to accept, to be honest, but it's kind of funny. But what is actually a Scala.js app, you might ask? Well, it's just a standard Scala app, turns out, with a main method. We make use of Laminar's render on DOM content loaded, which hooks a Laminar root element to an app DOM element in index.html. In the index.html, we also find load the Scala.js program here as an ES module. And this is here the app entry point generated by the Scala.js Vite plugin. So just as simple as that. Yes, I mentioned the name already several times. I'm using Laminar to build the app. Laminar is this really awesome UI library for Scala.js. I think it's a somewhat hidden gem. Maybe the closest in the JS world would be Solid.js. It also has similarities to Elm in philosophy. We heard about Elm on the first keynote. And in my app, I have some settings, panels, as you can see. They're ripe with buttons. So let's see how to define some buttons using Laminar. With Laminar, you first import the API. This gives you access to a kind of DSL to create DOM elements. So let's just create our button by calling button and the label. Of course, the next question is, how do you style this button? In my case, I've used Tailwind. Tailwind is a growing trend in the web. Basically, it's about using predefined classes to define the look of elements. It's called utility first design. Composable classes directly in HTML instead of custom CSS. And the Vite Tailwind plugin watches the file and generates the CSS corresponding to the classes. You can see how this works here, the Scala Laminar code on the left, with the page updated as we edit it. You might have spotted some IntelliSense support as well. This is via a VS Code plugin that you can configure to pick on Scala files. Actually, as it turns out, you can find entire component libraries built with Tailwind. Here you can see the documentation of the Flowbite library, and this is here the pop-up modal component that I use in my app. You can see below here, it's just HTML that you can copy-paste. Interactions come from custom Flowbite attributes and an associated GS library. This is ideally suited for building apps with Laminar, in my view, because it's straight DOM. And in these libraries, there are real alternatives to React components, which doesn't mean you cannot use React with Laminar. You totally can. You can also use web components, such as Shoelace, as we saw yesterday, and WebAwesome, for instance. Here's my how-to of how I use Flowbite. Basically, I just grabbed the HTML from the site that you saw earlier. I converted it to Laminar code, which is super easy because Laminar looks so much like HTML, actually. And yeah, the robot works pretty well for that, by the way. Then, if you want component behavior, well, either you re-implement it with Laminar, which is not necessarily so complicated. In my case, I actually included the Flowbite JavaScript dependency. So I just added this here in the index.html. And I defined the custom attributes that are used by this library and expected on the DOM elements in Laminar. So Laminar lets you define custom elements, custom attributes, sorry. What I like in this approach for components is that I can pick and choose just what I need, and it's also super easy to tweak. Okay, let me press this button now. This lets me introduce an important syntax element from Laminar's DSL, the arrow. This is here a method that registers an event listener that will log the mouse button. It's kind of an underwhelming example, I know, sorry about this. The problem with buttons is that they are often domain-specific, like plant a tree or launch a rocket. So in order to continue speaking about Laminar arrows, let's keep looking at our orthogonal internationalization example. So now you see the arrow pointing in another direction towards the text of the button. This apply changes button indeed needs to adapt dynamically to the language setting. And the leftward arrow is actually Laminar's subscription operator. We are here subscribing the text property of the button to language changes of this particular label. This internationalization dollar expression is a Laminar signal coming out of locale state. So let's now move on locale state. Locale state is a trait that has a current translations, Laminar var. This Laminar var is not to be confused with Scala's var. The var here represents mutable state, yes, but that can be observed. It contains, in our case, all labels for a certain language. And so from this var, we can derive a signal that allows us to subscribe to changes, as we have just seen before. So we mentioned streams, signal, and var. These are some of the fundamental abstractions in Laminar. They are observable, meaning they support higher order stream-like operators. And my mental model around them is that they kind of stack in increasing order of capabilities, not to be confused with Scala's new capabilities. But yes, at the level of the event stream, it's just something you can subscribe to, and it's a sequence of discrete events. Then signal introduces a notion of state. You have a current value at all times. So it's kind of a reified time evolving value. And var is a signal which value you can set directly via a call. You might ask, how does Laminar manage all the subscriptions in the app? Well, the way it works is that by using Laminar's DSL, we are building a hierarchy of elements parallel to the DOM. And Laminar managed elements have a common root node. Laminar is tracking when elements must be mounted or unmounted from the DOM, and thus subscriptions activated or deactivated. It's important here to mention that this is not a virtual DOM with diffing mechanisms like in React. So Laminar with these mechanisms allow for functional reactive coding style, also commonly known as the acronym FRP, for functional reactive programming. Continuing our example here, we are reacting to language change by retrieving translations, which is another stream. I'm calling this a behavior, by the way. That's just something I came up with in terms of naming, so nothing standard. And to do this, we use a high-order FRP operator, flat map switch. You find a similar operator in RxJS, if some of you are familiar with it. Switch in flat map switch means that the stream mirrors the inner stream. So let's say we have a language menu, and we set the language to French. We get a FR event on the current language var, and flat map switch launches an inner stream which retrieves the French translations via the internationalization service. In the implementation that I have, this is an async call to the API. When we get the translations, we set the corresponding var in locally. And notice that this is a stream. So if we poll at regular intervals, we can get updates from the backend. Later on, if we switch to English, there's another event on the parent stream. And we switch to the new inner stream, the English stream. Note that events propagate further through the observable graph. So when we set the current translations in locally, this is a var, and it will trigger other events downstream, such as updating the button label as we coded before. Behavioral logic is what I generally like to have unit coverage for. In this case, the logic is pretty trivial, but I'm just showing how you can use your traditional testing tools from the Scala ecosystem. This is here an munit property test, making use of Scala check. I don't have time here to get into the details, but this property verifies that for all translations, the current one matches the language. If you ever have coded UIs, you will probably agree that managing state is a big deal. So this diagram shows how organized state and how with signals we can create a graph of behaviors reacting to events and state changes. In state, we have all application state. And what I call behavioral logic listens to signals. It might set elements of state, which in reaction might trigger other signals, etc. Then you have what I call UI components. These components are relatively generic and also have elements of state that are local to the component. Behaviors describe how local state is wired to global state via signals when mounted, and vice versa describes how events influence the evolution of global state. So in summary, what I call behaviors act a bit as a switchboard in the app. And the application state you potentially save in local storage or on the server. The local state is more ephemeral in nature and only relevant when the component is mounted. Anyway, that's how I organize things, but you could do this differently. As a matter of fact, with Laminar, you have full flexibility on how to organize your code. You can even replicate the Redux pattern for more complex processes in your app, like in a piecewise fashion. So this piece of code is a fully functional Redux implementation. So I'm not going to dig into the details here, because it's a bit of code. But it's just to illustrate how flexible this is. I personally find Redux useful to define behavior with a strict state machine when interactions become complex. And I'm actually using this for an editor component in my app that has a lot of state and possible interactions. Another big topic is how to piggyback on the massive JS library ecosystem. So a number of wrappers exist for mainstream libs, or you can write your own, but that's kind of tedious. So what I'm using, and is absolutely great, is Scala.type. Scala.type is a SBT plugin that can generate Scala wrappers from TypeScript definitions automatically. In fact, as you've seen from the videos, it's a map-centric app, and I'm using MapLibre. MapLibre is a big JS component. It's a fork of Mapbox that supports WebGL rendering. And MapLibre expects to be hooked in a DOM element. So we can hook it into a Laminar managed element using this method here with a very long name. But essentially, that allows defining mount and unmount callbacks. So with this embedder that we just defined here, we can simply, at a usage site, hook it into a Laminar div. Just like that, we get MapLibre in our app. I showed earlier how we retrieve translations when there is a language change. And as we briefly saw, this abstraction of service allows for unit testing. So now in terms of its actual implementation, you'll also remember we defined endpoints with Tapir. So our implementation mixes in the endpoint definition so that we can interpret it using the HTTP client with a fetch backend. I'm not showing here how we could poll with a scheduler to allow for translation updates, for instance. But this is a stream here, so you could totally do that. Let's see this code in action. We can set a breakpoint where the API is called. This is then switching the language to French, and you see how this gets called. We can see values of local variables, and if we move up the stack one notch, we see our French flat map switch. So all this talk of API gets us closer to the backend. We fuel the backend with the type level stack. It's been around for a while now, and it's in production in many places. Cat's effect and the IO monad gives you full control, of course, at the cost of a certain learning curve. For the web server, it's HTTP4S, and since I needed HTTP2 support, I'm using the Netty backend. FS2 is the streaming library in type level running on IO, and I'm using this from my tile server, as well as I'll describe shortly. So how do we build an HTTP4S server with Tapir? Here, for the sake of simplicity, we'll only implement our internationalization endpoint. This is a cat's effect IO app. We mix in the endpoint definition. And the entry point is the run method. We first define the app resource. This needs an internationalization service, for which I'm using a small, nice library called Babel, hence the name here. And when we have this service, we can then instantiate our server. We'll see just below how we do that. Then we just say that we'll use this app resource forever, that is until program termination. Here's how we define the server. We get an interpreter for the Tapir definitions. We use the Tapir DSL to define the endpoint server logic. In our case, this is just delegating to our internationalization service. We get the HTTP4S routes for this endpoint, which we decorate with all kinds of middleware. More on that shortly. Then we can just wire our server using the Netty implementation. Yes, all kind of middleware is available for HTTP4S. Of course, you can also define your own. Middleware intercepts requests and responses, and you can see some keywords here of things that are readily available. You can see cores, timing, dating, JZip, logging, common, etc. So I went full speed on this one, but it makes it very easy to essentially benefit from all these capabilities in your endpoints. Okay, sorry in advance. With this video, I'm going to be waking you up. This was intentional. But remember, I told you I needed a tile server. Basically, to create an interactive map and navigation experience, MapLibre is constantly issuing get tile requests over HTTP2. And so if you typically zoom in and out in quick succession, it's also able to cancel them, which you see on the right in red. Okay, sorry about this. So this sequence diagram shows the interaction between MapLibre all the way into the DB. So you see the tile request here over HTTP2. It gets to the application load balancer over HTTPS. The AWS load balancer has a built-in certificate. You don't need to manage it, so it's super convenient to have termination happening here. And so the tile request is forwarded to a server instance via HTTP1. On the instance, I have an envoy proxy sidecar to upgrade HTTP1 to HTTP2. You might say, why? The reason, and the sole reason I'm doing this, is to allow for reliable termination detection. And then we use a specific PostGIS function to retrieve a tile in binary format. This is all done in a streaming fashion, and if we get a reset stream on the HTTP2 connection, cancellation can propagate all the way into the database, culminating in a GBC cancel request. Code-wise, we implement this with FS2 and Doobie. We are here defining a stream of chunks of bytes, forming up the tile. We use the Doobie DSL to define what is called an SQL fragment, here abridged. But you can see this primitive from PostGIS, st as mbt, which produces a tile. We indicate we want to stream this, and then the layer tile function interprets it on I/O using the transactor. Transactor represents our DB connection, and so out of this, we get now a stream of bytes that we can directly feed into the HTTP response. So that's how we wire this tiling endpoint. We use, in this case, the HTTP4S DSL for defining it. Then we just basically wire the function we saw earlier. And notice here how HTTP4S directly accepts an FS2 stream as a response. Therefore, cancellation resulting from connection termination all the way from the client will thread its way through the stream chain. Okay, so now we have our server. How do we package it? For this, I'm using another SBT plugin, SBT-gib. You can define all kinds of properties, such as the base image, etc. But one thing worth mentioning here is how I package the client. You can see that I picked the output of the Vite build and put it into public, quite simply. The output of the Vite build is just really a bunch of JavaScript. There's no magic there. And I'm just including those files in the container. For these static files, I'm actually using HTTP4S itself, not a separate server, with the static route. But okay, clearly building the container isn't the end of the story. We need to deploy that stuff. And this is the moment where you might say, oh darn, will I have to touch some YAML? Because show of hands who like me suffer from YAML allergy. Some of you. You know, red eyes from detecting the wrong indent, typos, all kinds of weird templates, special charts. Anyways, for you guys, I have some good news. Witness here a standard Scala program. This is a program that will deploy your server. The most relevant import in this program is Besom, of course, the fantastic Pulumi driver from Virtuous Lab. I'll explain more about what is Pulumi shortly. But yeah, the first line shows that we are defining this Pulumi program. And we start by loading up a bunch of config. We'll see later where the config comes from. But you see some, kind of infra names such as ECS, networking, Datadog, database, container, etc. So we are loading up all these values so that we can call a constructor. This is a Nexus service constructor, something custom that I coded, which will create a Fargate service, but you could do that for Kubernetes as well, of course. And inside of that, you have all the infra that is done. We'll see a bit of that in the next slide. Out of this call, we get the Fargate service. This is a type, actually, from Besom, AWS import. And this is wrapped in an output monad. That's Besom's main abstraction for things that need to exist in the infra space at the end of the program. At the end, precisely, pulumi.run expects a stack instance with all the outputs we have provisioned, in our case just service. And we can also export some particular values. These can be reused in other stacks. So let's have a quick look inside of this service constructor to give you a taste of what it feels to code in Scala your infra. So our imports are a bit more precise here. We are importing Pulumi's AWS provider. And this is here a constructor for a generic Fargate service with my kind of recipes and source. All resources in Pulumi always have a name. This is used in the Pulumi state. We speak about this a bit more later. And so we accept our service name here. We have our configs injected. They were in the given scope. And then we create and assemble each sub-resource in turn. So it's kind of a drawer pooling exercise here. We start by the container. You can see that we are grabbing the image from our config. This lets us then define the task, the Fargate task, which uses the container. And finally, the service instantiation itself. And all along, Besom types guide us in doing the right thing, which is really great for an infra newbie like I was, like I'm a bit less now, thanks to this. Yeah, let's just step back one step. I jump straight into code for effect. Pulumi is open source. You can run it yourself, or you can pay for the hosted service from the corresponding company. And Scala isn't officially supported by Pulumi, but thanks to folks at Virtuous Lab, we have Besom. Libs are generated for all available Pulumi providers. You can drive all sorts of infra, really. And available in Maven Central to be imported in your projects. And on the whole, we could say that all this setup allows for type-driven infrastructure, which is kind of a cool concept. How does it work? Well, we have our program written in Scala using the Besom SDK, as we saw before. Then we can, for instance, create a GitHub workflow or any kind of workflow which makes use of the Pulumi CLI. Of course, you can also use the Pulumi CLI locally in your shell. And running the program makes use of the Pulumi Besom plugin that allows it to interpret those Besom Scala programs. Running the program makes use of providers to drive the actual provisioning. You can see AWS provider here, Datadog provider. It also keeps the state in the Pulumi cloud, that's the paid service, or in your own storage, for instance, S3, that works very well. So you can see we have state where each resource that created is kept track of. And it also grabs configuration from Pulumi-esque or config files or environment variables. Pulumi-esque, more about it shortly. It's a Pulumi service as well. If you pay for the Pulumi cloud offering, you get a nice dashboard when you can see all your stacks, your resources, etc. What's also cool is the previewing ability, showing you what will change if you merge your PR. And I mentioned Pulumi-esque. This is a secure repository for config values, static and dynamic, and secrets. You can see a screenshot of the VS Code integration here on the left. You can edit your configuration directly in a secure way. And on the right, it's kind of a zoom in on this. You see the configuration values, for instance, for the DB, the instance type, the Postgres version. And then under Pulumi config, you can see the values that we were loading earlier in the program. Nobody reacted. This is YAML. Very sorry, I tried to sneak it underneath. But it's just key value in this case, no template, whatever crazy magic. But yeah, we're back to a little bit of YAML. But you can do your configuration otherwise. So these are exposed, as we saw earlier, in config.require in the Scala program. And yeah, again, the Ask is just convenience. You can use files, environment variables, etc. Besom has a great tutorial using the Scala CLI. This works super well. For this project, I used SBT because I have a monorepo with multiple infra programs for sharing some assets, such as types. Yes, I'm actually using refined types with Iron for Besom programs too, for configuration safety. So no weird IP address gets in my infra code. And these are different programs using this shared project because they correspond to different GitHub workflows. In domain, I set up the whole domain, the DNS. In the core, I mainly take care of the database. In app, this is a bit of what you saw earlier, the server, the service, etc. Mainly here, what I want to convey is that this is standard Scala. You can publish and import libraries, have multi-project builds. Possibilities are endless. So as a takeaway, I hope I was able to give you a taste of what full stack Scala feels like. Yes, you can do everything in Scala. It's true. It leads to compact, efficient, safe, uniform code base from front to back plus ops. And I think it's great for product teams. It promotes alignment. Or for solo players, you master one stack, you can do it all. Scala skills are nowadays powerful everywhere, which is great news since I feel the AI age kind of calls for human generalists that can assemble things. And last but not least, it's also about enjoying what we do. We all love coding in Scala. So on this, I would like to give special thanks to the library authors and contributors that make this joy of coding in Scala possible day to day. And of course to the Scala community at large. Thank you all also for your attention. Thanks to Scala Days for the opportunity. And yes, we still have some time, I think, for questions, either now, or you can come in the hallway at all times later. Feel free. Thank you.
Thank you very much. It's working? Okay. Thank you very much for the talk. Question about your Scala team, basically, that works with you, the other engineers. Usually, we are now kind of put into backend projects, most of us. How was for you and for the others to enter this new full stack, everything cloud integrated, fascination, dream, unicorns and rainbows? How did you handle it to expose them to front end, to ops, to all these new tools?
Yeah, thanks for your question. So it was a journey. Basically, on the front end, I didn't really know where I will end up. So I started exploring all this, and that's also why I compiled this talk, just so that you also can benefit a bit. And what I finally realized is, okay, once you know a little bit some of the things you might use, then everything works quite well. And for instance, if you take Laminar, it's extremely well documented. It's quite dense, but there's good documentation. Nikita, the creator, is very helpful on Discord. So honestly, so far I haven't had any issues. You have your debugger working and everything. And then in terms of UI, nowadays you find a lot of resources online. So for instance, those component libraries, they make it relatively easy to, put something together. If you have a design team, of course, they might give you some design system so you can replicate that. Then infrastructure-wise, what's great about Pulumi is the docs. So Pulumi has docs, which are quite indicative. And also the types, as I was saying. So when you start creating basically your resources, the types will indicate what you need to configure. And overall, the fact that you don't have to, you're in a familiar environment where you have programmatic, power, You have IntelliSense. You know, it's not like you're browsing through tons of YAML with a lot of duplication, for instance. The whole thing is kind of empowering. I felt super good about, you know, finally being able actually to touch on all the pieces. Now I feel I can do basically, I put together any system. I've just recently deployed some AI models, for instance, using SageMaker with Scala, you know, to just, so I strongly encourage you to take the leap and try. There are some good. So at the moment, I'm still alone, so I cannot hide this. Yeah, because it's an early project. As I was mentioning, I'm building the system, but I soon hope to be able to have some budget for hiring more. I think we had these messages yesterday also about how, you know, if you put lay the foundations, Scala is actually pretty approachable as a language, and you can totally ramp up people on this. And the fact that on the front end, it actually connects with the traditional JavaScript tools. You can use libraries, as I showed, makes it also maybe easier to get in from someone that would have this kind of experience beforehand. I hope this answers a bit, but yeah. My pleasure.
Yeah, that's all the time we have. Thank you very much.
All right, but don't hesitate again. Thank you. Thank you.